In modern cars, data is just as important as gasoline or electricity. Advanced driver assistance, high-resolution cameras, over-the-air updates, and immersive infotainment all depend on fast, reliable communication. That's where Automotive Ethernet comes in. In this video, we'll break down what Automotive Ethernet is, why today's vehicles need it, and how it's reshaping in-vehicle networks. Traditional in-vehicle networks like CAN and LIN were designed for small, low-speed messages, perfect for window controls or engine management. But now, vehicles must stream video from multiple cameras, fuse data from radar and LiDAR, update software remotely, and keep passengers connected. The bandwidth requirements have exploded. Automotive Ethernet delivers higher data rates, scalability, and compatibility with IT and cloud technologies, making it the backbone of the software-defined vehicle. Ethernet is the dominant networking technology in IT and industrial environments. At its core, Ethernet moves data in frames over physical links, often organized with switches that forward traffic only where it's needed. Automotive Ethernet adapts these same principles to vehicles. It still uses frames, MAC addresses, and switched architectures, but it's optimized for automotive requirements like low weight, electromagnetic robustness, real-time behavior, and strict safety standards. Several automotive Ethernet standards define different speeds. 100 base T1 offers 100 megabits per second over a single twisted pair and is widely used for sensors, ECUs, and some cameras. 1000 base T1 brings 1 gigabit per second for bandwidth-heavy applications like high-resolution cameras, domain controllers, and infotainment backbones. Newer multi-gig variants push further, enabling 2.5, 5, or even 10 gigabits per second over automotive-grade cabling. All of these standards are designed to withstand vehicle temperature ranges, vibrations, and electromagnetic noise. Unlike traditional office Ethernet that often uses 4 twisted pairs, Automotive Ethernet typically relies on single-pair twisted cables. This reduces weight, cost, and space, critical factors in vehicle design. The physical layer, or PHY, is engineered to transmit high-speed differential signals over long cable runs while resisting electromagnetic interference from the powertrain, motors, and external sources. Standardized connectors and shielding ensure reliable connections in harsh automotive environments. Legacy in-vehicle networks like CAN and LIN use a shared bus topology. Every node listens to the same communication line and messages are broadcast to everyone. Automotive Ethernet moves toward switched architectures, where electronic control units connect to Ethernet switches in star or tree topologies. This allows higher aggregate bandwidth, improved isolation of traffic, and more flexible network design. Instead of every message going everywhere, switches forward frames only to their intended destinations. In a switched Ethernet vehicle network, domain controllers, such as for powertrain, body, infotainment, and ADAS, connect to one or more central switches. Traffic between sensors, ECUs, and actuators flows through these switches, which can prioritize certain streams and segment the network. This design supports modularity. Engineers can add new features or ECUs by attaching them to switches rather than reworking an entire shared bus. Vehicles contain both best-effort data, like music streaming, and time-critical data, such as control signals for braking or steering. Time-sensitive networking, or TSN, is a set of Ethernet standards that adds determinism. TSN introduces time synchronization, scheduled traffic, and prioritized queues so that critical frames are delivered within strict latency and jitter bounds. This lets Automotive Ethernet handle real-time control alongside less urgent traffic on the same physical network. For functions like adaptive cruise control, automated emergency braking, or lane keeping, delays of even a few milliseconds can matter. TSN-enabled Automotive Ethernet ensures that control messages arrive on time, every time, even when the network is busy with video, diagnostics, and infotainment traffic. Engineers can reserve bandwidth and schedule packets so that safety-critical data always has a clear path through the network. Automotive Ethernet enables rich infotainment experiences, high-resolution touchscreens, rear-seat entertainment, app stores, and seamless smartphone integration. High-bandwidth links between head units, amplifiers, and connectivity modules ensure smooth audio and video streaming. Because Ethernet is widely used in consumer and IT worlds, it's easier to integrate external devices and cloud services into the in-vehicle experience. Advanced driver assistance systems rely on a constant stream of data from cameras, radar, LiDAR, and ultrasonic sensors. Many of these sensors produce large amounts of data, especially high-resolution cameras used for surround view and perception. Automotive Ethernet's higher bandwidth supports these data streams, transporting them to ADAS domain controllers where algorithms fuse the information, detect objects, and make driving decisions. Over-the-air updates let manufacturers patch software, add new functions, and improve performance long after a vehicle is sold. Automotive Ethernet provides the internal backbone to route these updates from a telematics or connectivity unit to individual ECUs. High bandwidth shortens update times, while robust security mechanisms help ensure that only authenticated, verified software is installed. Because vehicle networks carry safety-critical data, Automotive Ethernet must be designed with functional safety and cybersecurity in mind. Redundant links and paths can protect against single points of failure. VLANs and segmentation isolate critical ECUs from less trusted domains. Security features like secure boot, encryption, authentication, and intrusion detection help guard against malicious attacks, unauthorized access, and tampering with network traffic. CAN remains extremely effective for low-speed control tasks and simple sensor data. It is robust, inexpensive, and well understood. However, its limited bandwidth and broadcast-style communication make it unsuitable for high-data applications like video or bulk updates. Automotive Ethernet offers more bandwidth, flexible topologies, and compatibility with modern IT infrastructure, though it typically costs more per node and requires careful network design. LIN is ideal for simple, low-cost functions like window switches or seat controls. It's slow but extremely economical. FlexRay was designed for time-deterministic, safety-critical applications and supports higher speeds than CAN, but it's more complex and has seen limited adoption compared to expectations. Automotive Ethernet, especially with TSN, can absorb many use cases from both FlexRay and high-end CAN, enabling a more unified, scalable network across the vehicle. As vehicles advance toward higher levels of automation and richer infotainment, bandwidth demands will keep climbing. Multi-gigabit Automotive Ethernet will support ultra-high-resolution cameras, detailed 3D maps, and continuous data logging. This evolution positions Ethernet as the primary infrastructure for future data-hungry applications inside the vehicle. To simplify wiring and reduce complexity, manufacturers are moving from domain-based architectures to zonal architectures. Instead of each domain running its own dedicated harness, local zone controllers handle all devices in a physical area of the car. These zones then connect over high-speed Ethernet backbones. This reduces cable length, eases assembly, and makes it easier to upgrade or reconfigure the vehicle's electronics over time. Automotive Ethernet is a key enabler for software-defined vehicles, where most functionality is implemented and updated in software rather than fixed in hardware. High bandwidth, flexible networking allows central compute platforms to orchestrate features across many ECUs and sensors. Over time, this will support new business models based on subscriptions, feature unlocks, and continuous improvement through software rather than hardware changes. Automotive Ethernet is quickly becoming the nervous system of modern vehicles. It unifies communication for infotainment, ADAS, control, diagnostics, and updates into a high-speed, scalable, and secure network. As bandwidth grows and architectures evolve toward zonal and software-defined designs, Ethernet will play an even larger role in how vehicles are built, updated, and experienced. Understanding automotive Ethernet today means understanding the foundation of tomorrow's cars.